Okay, thanks for coming for this reading group. So basically today, so I have read this paper. It's called Open the Black Box of Deep Learning Neural Networks via Information. Basically, it's a group that's dedicated to actually understand what the neural network is actually about. And they want to, so basically we need some mathematical tool to do that. For example, we can think deep learning as a mapping from input to output. We can also think of it as a mapping between input distribution to output distribution. So basically this paper is trying to use the mathematical tool of information theory in order to understand the deep learning, so which is their approach. So firstly, let's consider some following questions. The first question is, why does deep learning with stochastic gradient descent scale reasonably with the complexity of the problem? So this could be a trivial question if you think about it, but it's actually not that trivial because as the complexity of problem, let's say, is doubled, wouldn't the solution be exponentially increased with the complexity, or actually scale linearly with the complexity? So it turns out that deep learning DAN must scale reasonably well with the problem. When we were talking about the complexity problem, it's more like the cardinality of the hypothesis space, and I'll try to explain that later on. The second question is the stochastic gradient descent is a first order approximation. Experiments show that some second order methods and a noisy version of the first order methods usually don't really work. And we are interested in why is that. Also, essentially, we want to know what is really happening inside the deep neural network. We need some theoretical tools to unravel the myth. So firstly, we have to look at some dry information theory basics. Firstly, this is the definition of the entropy. Basically, it measures the uncertainty within distribution. And more importantly, we have the mutual information. So the mutual information of x and y is basically, for example, is basically if I know what's happening with y. So how many entropy we can take away from the system of x. Basically, this is the mutual information of x and y, which is the chaos divergence between their distribution and and between the products of their marginal distribution. Basically, is the definition of the mutual information. Also, there's important theory of data processing inequality. If we have a Markov chain, for example, x to y to z, this is similar to when we process data through a deep learning neural network, where the x is the input, y could be some intermediate layer, and z could be the output. Basically, what this theory tells us is that basically, for example, if I have some neural network, right? So this is the second layer, this is the third layer of the neural network. What this theory tells us is that the information contained by this layer so contained in this layer represents this layer. So basically, this is going to contain less information than this as we process along this pipeline. Does that make sense? So if you don't have the information theory background, it could be slightly. So basically, think about that I have an image. I process using something, but the thing is, during this processing, I actually lose the information of the original image. If you process along, then you lose more and more information of the image. So essentially, in the end, we actually end up with very little information of the inputs. Yeah, so this is the mutual information. So basically, the last theorem is important in this paper, but it's not that important to understand. So basically, it's called asymptotic equipartition property, which what it's saying is that if we have a bunch of IID, random variable, they all belong to the same distribution, then eventually, doesn't matter what's the value of x1, x2, and xn, the probability to have them is going to be the same. So basically, it is very similar to strong law of large number. It's a typicality argument where that essentially, if you have, for example, millions of images, then we assume that for some particular case to happen, they all have equal probability. But sorry that I'm not an expert of information theory, but so basically this plays an important role in deriving the formulas, but it's not important to, but it's not that important for us to understand this work. Okay, so here is basically data processing inequality in deep neural network. As we can see that, for example, there's a lot of uncertainties or possibilities in the images. But the mutual information of the hidden layer will be actually smaller than the original information. So basically, this information is smaller than that. And if we go along different hidden layers, if we go deeper and deeper, essentially what's happening is so it's larger or equal to. So unless this hidden layer is a one-to-one function of x, that's only when we contain all the information. But if it's not an invertible formula, then we lose some information eventually. Okay, so eventually it's go along this chain and we lose more and more information. Then you might be asking this question. So eventually in the end layer, we actually know very little about the input. Why would many layers actually help me learn, right? So if you have many layers, that actually decrease your information about the input. Why would that actually help us? So this is what I'm trying to explain. And this is another idea. So previous is idea of information, and this is a concept of encoder and decoder nature of hidden layer. So what we can think is we can think like this. For each different layer, for example, let's say this particular layer, anything that's before this layer is actually encoded, and anything after this layer is a decoder. So basically, this part is the encoded information of our input, and it does encoding. This is some sort of representation of the inputs. And at this layer, for example, the complexity of the encoder is very small. And if you move, and the complexity of the decoder is very large, basically. If you move along, for example, at the very last layer, what's happening is you will have a very complex encoder and very simple decoder. And the author states that there's actually, although it's very complicated, but there are actually only two important characteristics. And besides, if we know these two characteristics, we understand deep neural network. And these two characteristics is firstly the mutual information of a particular layer and the input. Basically, this means how much information of this layer I contain about this input. Basically, that's what it means. And the second important property is how much information this particular layer I contain of the label. So basically, it's more like a classification problem. Let's think of a more classification problem, but it doesn't have to. So as you can see that, so let's move to the next slide. Yes. So basically, what it means is if you have some sort of large, if your end layer, so basically now we only consider about the end layer, your final representation of the image. If this end layer has rich information about the input, what's happening is that's essentially you just put the original image into the neural network, which doesn't really do anything. So, but it will do something. For example, I have only one layer network. which is very, very large, but it's possible. Let's say I have one layer network. Then what's happening is this network has a rich representation of my input. But what's going to happen is I will need so many examples. I will have to show it all the patterns in order for it to actually give me a good prediction. So large mutual information means high sample complexity, which means I have to feed into very complex sample. So basically we don't want that. That's why we actually want to decrease it. However, large information, so basically if my representation has a lot of information about a label, that's actually good for us because this will lead to high accuracy. So basically we have a trade-off problem in the neural network. On one hand, we actually want to lose the information about the input. On the other hand, we want to gain the information about the label. So it's a trade-off. So this author, he thinks in this way, in this particular way. So this is, okay, so basically, as you can see, the important thing here is we want to estimate the mutual information. So you don't have to read this, but so I'm just give you a gist of it, how they estimate. Basically, they bin the values into quantized regions. So basically, we cannot estimate mutual information of the mutual information was sort of created by Shannon. So basically, it's more like discrete regions. So we want to bin the values into quantized regions, so we can calculate the mutual information in terms of bits, in terms of entropy. Firstly we have to discretize, then we use some formulas. This paper actually tells you how to do it like that, but we will skip that details. So here is like the most important discovery of this paper. I want to actually show you a video instead of just the picture. So I'll load this YouTube video. So basically, before that, I want to explain. So basically, this is the mutual. So the x-axis is the mutual information, is the information of the representation contained. The information of the input contained by the representation, and the y-axis is the information of the label contained by the representation. And this different color. So this orange color here represents the last layer of the neural network. And this part is the middle layer, and the blue part is the first layer, for example, of the neural network. As you can see, you don't even have to train the neural network, but it will contain, the first neural network is going to contain all the information about the input. It's going to contain all the information about the label, because it has all the information. But the problem is, like I said, if you have some sort of that layer, although it has very good information, rich information, but we need very high sample complexity to train that. So it's not ideal. And naturally, because all the weights are random, everything is random. So down here, the last layer network actually doesn't know anything. It doesn't know anything about input. It doesn't know anything about the label. Basically, that's before training. And let's have a look what happens when you train. Okay. So this is just the video, and here I have screenshot the most important process of the thing. So basically, what's happening is, so let's focus on the last layer because we only have so much time. So if you look at the last layer, during training, and this I remember is 300 epoch. It's like very little amount of epochs. What's happening is the information, what's happening is information of the last layer, well, it increases. We expect it to increase. So actually, so up to this part, so I'm going to actually draw something out of my mind. So basically, we have a training era, that's time, that's epochs, or that's epochs. Let's say this is epochs. and this is actually the training error. What's happening is the training error, it drops along here. So here is, for example, 300 epochs. And eventually, basically, we have 10,000 epochs. And at this 300 epochs, we have the final layer of the neural network actually gains a lot of information about the input and gains a lot of information about the label as well. But what's really interesting happening is after this training error, eventually it's actually converged. So here we don't actually have that much of difference in training error. But the problem is in this time, what's happening is the final layer is actually trying to forget about the information of the input image. So it's actually trying its best to, as you can see here, of course, the final layer still contains a lot of image of the label, but it forgets the information about the input image. But of course, you can't forget everything, but you want to forget the most irrelevant thing. For example, the backgrounds, the color of a cat, which it doesn't. So think about that. So the author argues that this period is actually the most important part of the neural network, although the error is converged. Let's, for example, here we just stop it. Okay, we stop that neural network, and we have a good accuracy on training set. But if we take that neural network on a test set, it will work very badly because it has not generalized, because it learns too much information about the input, which is actually not relevant to the label. So if we actually take this part and we put in the test set, we will get bad results. So, well, that's according to the author. And along this part, we actually get rid of forgetting. So here is more like memorizing. Here is more like forgetting. We forget about the relevant features of the input, which it can actually generalize in the So this is the phenomenon. So this author is very mathematical. He actually wants to explain why that happens with some neural network. Here is some math that we actually have to explain a little bit. So the first thing we want to know is there's something called generalization bounds in learning theory. Basically, generalization bounds. This pen actually, yeah. Generalization bound is basically on the test error, so not on the training set, but on all possible. So, for example, if you reach very little error in the training set, but that doesn't mean you have a small generalization error. You could have a huge generalization error because you overfit it. So basically, if you're interested about this theory, it's something called PAC. It's something called PAC theory. It's called probably approximately correctly. So basically, we want to have we want to have little generalization error with high probability. It's a theory in learning theory. Basically, the author says that the confidence in this formula doesn't really matter because we have so many learning examples. Eventually, the confidence will be 1. If confidence is close to 1, then this term is basically 0. So that doesn't really matter. So, but we want to know what's the epsilon color of the hypothesis class. But what that really means, okay? So this is actually not very trivial to understand at the moment, but I want to briefly explain that in discrete case. So basically, this is continuous space where we have epsilon color of hypothesis class. But I'm trying to explain it in discrete case. If you understand that's already enough. So basically, think about. So basically, I'm trying to explain this. What this means is it's cardinality of hypothesis space. Is cardinality of hypothesis space. What does that really mean? That's actually measures how many possible functions of the neural network. So for example, I have 1 billion parameters. How many possible functions could that be? That could be a lot of things, right? So we use this cardinality to estimate. For example, if I have 1001, if that will give me 1, if, for example, I'm just making some arbitrary example, that gives me 0. So the output can be 1 or 0, and the input can be a 4-bit input. If you want to fit this one with minimal neural network, the cardinality, because the input is, we have 2 to the power of 4 possible inputs. The output is 2 possible outputs. Eventually, the cardinality of the hypothesis space is actually 2 to the power 4. So basically, is the possible output to the power of possible inputs. That works in discrete case. So epsilon cover of hypothesis class is basically cardinality of hypothesis space in a discrete form. Basically, epsilon cover is more like we cover this continuous space with ball that has radius of epsilon. Anyway, it turns out that this thing is going to be some sort of similar to 1 over epsilon to d. What is d? D is the VC dimension of the D is the VC dimension of the algorithm. Yes. So basically, if your algorithm has a lot of parameters, it has higher VC dimension. It has higher VC. If you're interested, you can actually look into it. Well, it explains, right? So basically, your size of the function increases with the complexity of the functions you have. The important part of this generalization bound is if you actually substitute this one inside. If you put this one inside, you actually, the log and the exponential part sort of just disappear. So eventually you have d over 2n. D over 2n times logarithmic of that, and the other term doesn't really matter. So in this case, as we can see, what's happening is this is the bound. If my training example is small, this will be magnitudes larger than that. What's happening is I don't have a bound because this thing is essentially, it has to be smaller than 1 for it to work because it's error. So the problem is these two things, they must be in similar order. And if my training examples is more than my complexity, the algorithm has a bound, has a generalization bound. Otherwise, it doesn't have a generalization bound, so it doesn't generalize. The problem of this model, which people use to explain deep learning, is that this model essentially doesn't work at all. The reason that is for deep learning, we have really, really complex model. That the cardinality, so the complexity of the model is very, very high. And the training example is small compared to that. I don't have the number here, but for example, this one is like 1 billion, and we only have 1 million example. Which means it shouldn't generalize on a test. It should always overfit the training set. So based on this old theory, is that it should always overfit. Which the author denied that this will work. So he comes up with something new. It's called new generalization bound. So in this new generalization bound, basically what's happening is instead of we use this one is cardinality of hypothesis space, but the author says no, we don't want that. If you use that, it doesn't work. Instead this thing, I don't want that, but instead this thing is going to be the number of possible ways of the input. Is basically the cardinality of the input space. So we don't look at hypothesis space, but instead we look at the input space, which is that. And also there's some theory in information that what he does is he cut this input space into different cells, into amount of cells. And this cells is, for example, if you have 10 different images pass through the network, and you get the exactly same representation, and that representation is the small cell, basically. If you have, but within that small cell, of course, that all images have to have the same label. For example, you have 10 labels. Doesn't mean you only have 10 possible representations, but for each possible representation, the images has to have the same label. Basically, that's the logic behind it. So the author says, okay, the cardinality of that is essentially the cardinality.
Is that for all possible network configurations or for a particular network configuration?
I think it's general. So he's trying to derive a general idea of what's the
Sometimes you have a training set in which the same input appears with two different labels. ImageNet, I'm thinking of you. Right? There are duplicates within ImageNet large-scale vision challenges with different labels. They're guaranteed, no matter what you do, to have the same representation.
Yes.
With different labels.
Yeah.
So there's a label noise problem in there. But I suspect this idea can be generalized by circumstances.
Yeah, so we could have, for example, this different label with a new label. But I think it's just trying to, they have to play with the toy example, otherwise it will just. So basically, the cardinality, okay, since we are saying that everything in that cell is identical, it's a homogeneous to, if they are homogeneous to the labels in these guys, it's actually essentially the same as we can just use that. So this is the representation space. So basically the size of the input space, instead we use the size of the representation space. Okay, so no, I'm trying to explain that. So basically, H is the entropy. H is the entropy of the number of uncertainties. Is the entropy of the X. If you divide by this thing by the entropy of the input space, given this partition. So for example, I figure out a way to actually cut this one into different. If you divide this thing, it will give you that. It will give you that. So if you this is basically the size of the thing, and this is the number of possible ways. 2 to the power of entropy basically is the number of different possible inputs. If you divide it by this, it will give you that. So if you want to absolutely understand, you have to look into the paper that they write. So this is where they use asymptotic equipartition theorem to prove this whole. But eventually, what's happening is if you do a division here, then it's actually minus on the top. So it's actually 2hx minus hx. This actually equals to the mutual information. This actually equals to, yes, the mutual information.
That's it.
Yeah. This actually gives you the mutual information of the X. Okay, so now we look at, sorry, it's gone, but I can write it again. So basically we have smaller than this log h over 2n problem. Remember we have that bound. Now instead we put this thing inside. This is log base 2 because the information theory is log base. In log base 2 and the 2 to the power of that, eventually it's just that. And that is 2 to the power of that. So eventually you get 2 to the power of information p over 2n. So this is the important part of the theory. What that really means is if this mutual information is small, I'm going to generalize well. That's all it's trying to say. Actually, every bit I'm decreasing here, that means I only need half sample complexity. That is the important part of the theory. aligns with the behavior of the neural network. The behavior of the neural network is decreasing that. So this actually aligns with that. So here we actually, so here is the end of the sort of the theoretical bound. But we have two questions. And that's, after these two questions, that should be it. So the first question is, okay, I know that if I compress, it's going to be good. But is there actually a limit? And the second question is, why would the neural network be doing that? So that's the two questions. Okay, so let's look at the first question. So this is a little bit of information theory. Is basically, so just look at the first equation. Is Sx is basically a representation of x. So basically, what we want that we want that to be small. We want to be that very, very small. But we want that information that contains, so we want to minimize that, but we don't want to lose the information of the label. That's what it means. So it's minimal sufficient statistics. But this doesn't work in somehow, and they just do, they have a new relaxation. Basically, I want to increase, this is the representation, that's the input. I want to decrease the amount of that, and I want to increase the amount of that. So basically, they have this new relaxation to do that. But it's all right if you get that. But anyway, this is basically answer the first question: is there a limit? Yes, there is a limit. So they used, it's called information bottleneck methods. They calculated this black line here. And they claim that this black line is universally true. So it doesn't matter if it's brain learning or it's neural network learning or it is some other learning. This black line is universally true. For example, at this particular point, with that amount of information you know about inputs, there's no way you can gain more information of the label. There's no way. So they prove that there's no way beyond this black line. So that is called the universal information bottleneck. So you basically arrive there, you can't get more information. And this red line here is called a finite sample bound. It's basically, we are not going to get this black bound because we only have that much sample, remember? So the sample complexity, if you keep on going this line infinitely, what's going to happen is your sample complexity is going to be so huge, where you have too many samples that I cannot. So you have, you need a lot of samples to extract information about the label. So that's why if in the reality, basically, if you want to have more information about inputs, actually you are going to have less information about the label because the sample complexity becomes so huge. So that is why the red line is the bound of the reality. So basically, the neural network want to compress this thing. You compress, but if you compress, you hit the black one. You hit the black one, and the black one will not allow you to. If you go along, if you break this, so you can never break this black line. But you might be thinking, why can't we just go along this? So basically, I have less and less information. That's because we are training neural network by this error, by minimizing the error. So the neural network backpropagation, this error constraint, will not allow you to have lower accuracy. So basically, we have these two bounds. So that's the limit of the compression.
Okay. What if the output is in the input? So the input contains the output in vanilla and contains salt. Okay, it contains the output and the random numbers. So you can exactly get rid of the random numbers and compress the input so that the mutual information with the output is 1, but the mutual information with the input is decreased. And then if you compress further, you exactly lose information, you lose mutual information with the input and the output at the same rate. So that curve is going to go up in a straight line and then head across in a straight line. So when you get rid of all information, you have no information with either input or output, bottom left-hand corner. As you increase the amount of information you have, you do it exactly identically with input and output, because they're both there, until you've now got all of the output. And then if you keep encoding more of the input, you don't get any more output because you've got it all and you just get across. Right? Why, I don't see why that doesn't give you points above that black curve. Because the slope of that black curve at the beginning has to be 1. You know, if I grab one bit, I can hope.
I think I didn't explain that well, but I think what they say is that this black line is determined by the data. So basically, it's structure irrelevant, but data relevant. So maybe for the data you were describing, it will have a different black line. So I'm not sure if.
Oh, okay. Yeah, right.
So it's universally true for same data, but yeah.
What about what about when the input is like the same as the label? Like, so what about when X is the same as Y?
Yeah, so I think that means this black line will change. So this black line is universally true for same data. So it's only, so for example, you have a bunch of data.
Yeah.
Doesn't matter you learn it by your brain or you learn it by algorithm. You can't surpass this black line. But this black line will change if you change the data.
Okay.
I think that's-
Doesn't always have that curved shape then.
Yeah, it's possible it has this.
So this is only for like, say like a classification type of problem where you have like an explicit label that you can associate with some input data.
Yeah.
Yeah.
So I'm just gonna quickly finish that so we can
Yeah.
have more discussion. So, yeah, so that's the limit. So time to answer the second question. Just remind you, the second question is why would neural network be doing that? To be honest, it's some mathematics that I cannot. If you're interested, you can actually go into it. So basically, this is actually very important. So they argue that the learning thing, remember this learning thing, is can be separated by 2 parts. So the first part is what they call the drifting case. It's basically I have a neural network sitting at somewhere, and I know where I'm going to. The parameters, I know where to minimize the thing. This is the drifting. So in this drifting case, as you can see, the average size of the gradient is large, and the standard deviation of that is small. So remember, this is in logarithmic scale. So basically, they have a huge difference in the beginning. However, as soon as you hit this point, as soon as you converge, your training error actually starts to converge, what's happening is the neural network is not really going anywhere. Instead, it has very large standard deviation. They refer it to a lower signal to noise ratio. So noise becomes very large, and the signal becomes lower. So in that case, they argue that the second phase is the first phase is drifting. The second case is diffusion. So it's like a random walk of Brownian motion. They even argue that in this phase, the stochastic gradient, so they say that, remember the first question I said before the presentation is that why only the first order network will work and the second order network might not work. And they use some math to show that because only the first order network can have this sort of behavior, which is random walk or Brownian motion. So basically, this is their experimental results. They show that it follows this way. So they argue that the stochastic gradient descent, the loss, is not actually working. It's actually working as a constraint. So you can do random walk, but you can't make my error worse. Basically, so the learning is actually sort of like, the loss is actually acting like a constraint. So you can't get more loss, but you can do random stuff, basically, along this, yeah.
So if I'm going to apply dropout, will the same graph I need to the same or it's gonna change dramatically.
So what's your question?
I mean, if you are going to apply dropout basically introduce another layer of stochastic process, right? So which means in the later stage it introduce more random stuff.
Yep. I think I am not very sure about that because I haven't tested that algorithm myself.
So, yeah, I think dropout and weight decay,
Mhm.
all of those things are regularization methods. And it's because of regularization that the hypothesis complexity is a whole lot smaller than you might think it is.
Mhm.
Because it's not possible to gain, they're all effectively reducing the hypothesis space.
Yeah.
Because the stochastic thing means that, you end up with representations that look the same from different things, which kind of in the language that we were just going through reduces that, the complexity of the hypothesis space. Weight decay reduces the complexity of the hypothesis space of all neural networks. So I think, all of these things are things that do that. I think kind of what's partly missing from this discussion is the role that regularization,
Yeah.
the conditioning plays.
Maybe in a paper there is some discussion, but I haven't put that into.
Yeah, I'm not, yes.
Yeah, but anyway, so it actually is, yeah.
Just wanted to ask, so does this two-phase gradient descent, this graph hold for any type of data set, or is it?
Yeah, so the author argues that it's gonna be the same for other
A
programs.
large range, yeah. Data sets of any decent complexity. But you often see that, right? And that dotted line is where you drop your learning rate.
Anyway, it also explains that why dropout will work somehow. I think in some part of the paper, he found that, okay, so basically remember the previous thing we have, that learning dynamics. Basically, it was testing on 50 different networks, and they have very, very different network parameters. They end up with having similar amount of mutual information. So he argues that if you take out a neuron or you do something like that, it will not affect the information it contains, which in turn it will not affect the result of the outputs. But anyway, so this part, the Fokker-Planck equation can be described. I don't really understand that yet, so it's alright if we just basically they refer to this Fokker-Planck equation. That this equation actually consists of drifting and diffusion in the same equation, and essentially they say it's a Wiener process where it doesn't have any drifting problem. It only has diffusion. So in short, this process, so they argue that the second phase is Wiener process, and this process maximizes the weight entropy. So the random, if you put a random molecules in my hand, and now I release it, it will go everywhere and maximize its entropy in this room. So if you do Wiener process on the weight, so basically it's gonna go wherever it wants. Eventually, it will maximize the representation entropy. So I want to refer back to this thing minus h. Okay, so basically, if you maximize, this is t given x. So basically, we know that the representation doesn't come out from nowhere. It comes out from my input. So maximizing the representation entropy is actually saying that we maximize the conditional. It's more like a conditional. It's more like a conditional entropy given the input space. But the input doesn't really change. If you maximize this, in terms, you actually minimize this. So they argue that because of this Fokker-Planck equation or Wiener process, there's some link. This process, that is what the neural network is actually trying to decrease that. Yeah, so that's probably the end of my presentation. Thanks.
So that last bit you were talking about makes sense in the context of another explanation I've heard of why. So in that last stage, the neural network, the neural network is actually, the neural network is actually trying to decrease that. So it's trying to decrease the amount of information that it can store. So it's trying to decrease the amount of information that it can store. So you know, the loss is not going down much, as you point out. But what's happening is there's noise going into the system, you're shaking it around. And if you look within the space of, you know, the weight space of networks that kind of perform equally well, there will be these sort of thin, you know, there'll be a sort of a large region with little thin bits going off. And if you start in one of the thin bits and you get shaken around, eventually you'll end up in that large central area. And what SGD does is it actually explicitly seeks out large regions of weight space that all perform equally well, rather than tiny regions of weight space.
I believe they argue that SGD is more like a multicolor relaxation with a loss bound, that you can't make the loss larger.
Yeah, that's right. So yes, that's right. You don't go uphill, or you know, you go, yes. But because as soon as you go uphill, there's a gradient pushing you back down to the plateau. But the plateau might have a big flat bit and lots of thin bits, or the well might have a large flat base and then little thin bits that come off it. And if you have a marble sitting in there and you're sort of shaking the thing around, eventually it'll be rattling around in a large area rather than one of the thin little bits. And that actually means that locally there's a large distribution over weights that works. So if you imagine you could build a covariance matrix over acceptable weight deviations that still perform well, that covariance would increase because you could make more deviations to the weights at a good solution and it would still perform well than at a bad solution and still have it perform well. And that fact that you're integrating, you know, you can effectively then treat it as integration over a large set of possible weight settings as opposed to just the single weight setting that you have. And that tends to lead to better generalization. Yeah, it's all still a little bit, I mean, they may have opened the box a bit, but it's still a bit opaque. Anyway, thank you. That was really interesting. Meta point, it's really worth learning and understanding this information theory stuff, because it does give you a whole pile of insights into what's happening. You know, in particular, if you were using binary networks, you could then you have a very explicit, discrete. You know, you have a discrete set of representations. There's 2 to the number of neurons in a layer. You have a discrete representation of the set of possible networks, 2 to the number of weights of the network. So all of the regularization things are kind of built into that already. So you can still do noise, add noise to layers, which decreases the mutual information with the input. So,
Actually, when I look at, I think it's more like the way we can think about neural network. I think they test on toy example as well. So I think it's more like we look at this and what we can get out of it is some way that we can think about, with some mental tool that we can use.
yeah. I think I mean, a lot of toy examples are good for understanding things, but there's a danger which is kind of like the danger of thinking of high dimensional data as being a bit like low dimensional data, and it isn't. You know, there's a sort of a danger that your understanding of how the toy example behaves might lead you to oversimplified ideas about how the real example works. But you can find intermediate examples with just enough real complexity that it hurts the system. That might be part of the pathway. I like that animation. Was that a particular toy example, or
Yes, I think.
was that an MNIST type?
They say that the same. Okay, so in the origin, so they say that they have seen this pattern in many different complex volumes as well, where the mutual information goes like that.
Yes, it gets hard to measure in really big systems, which is why. But at MNIST, you might have a go, right? You might plausibly have a go at measuring the mutual information in MNIST or something like that. Yeah. Cool, thank you. I suppose you can try and the input from any given layer. And the better, you know, you can reconstruct the input really, really, really well, and there's a lot of mutual information. And if you can't, then there isn't.
I think this also shows that so there's use of natural learning, which is different from the characterization. So for example, for classification, we aim to lose so many information. That's the relevance. But for natural learning, it actually retains those information. That's even though these information are irrelevant to this label.
Right, yes, that might be a reason for that. So, can't stop anything. Yes, better. Cool.
Yeah, so you still want to be over on that accurate side of the plot,
Yes,
but you don't want to be.
you want to be up left.
Yes. No one's always
No, that's it, exactly. Yeah, yeah. You want to retain. But there's something else that happens with things like dropout and noise, which is that that mutual information gets smeared out across many neurons. Right? Because dropout affects individual neurons, you want to smear the information you want to retain. You don't want to embed pieces of that information uniquely in neurons. You want to smear them across neurons so that you can retain as, you know, so as much of it as possible in the face of dropout. And so that actually might be, in the end, a conditioning trick. Tends to sort of cause you to distribute information rather than concentrate it.
I think also adding reconstruction rules, because I've seen Yang doing adding reconstruction rules.
Mhm.
That could limit this process as well.
Yeah, yeah, well, so curiously, yeah, you want to have terrible reconstruction of the input with great reconstruction of the output.
That's why I was like trying to ask about
Wacky.
when the input and the label is the same. Like trying to.
Well, in that instance, yeah, but then you don't have any work to do.
Yeah, I was wondering.
A zero-layer network is fine, or a one-layer network, input equals output.
So this is more like for classification.
Yeah.
If the goal has changes, then this mutual information stuff actually have different contexts.
Yeah. Yeah. Interesting.